Hi everyone, welcome to my first lesson for physics, Introduction to Vectors. Let's get into this. So let's start off with contrasting vectors with scalars. Fundamentally, a vector is a quantity which has both a magnitude and a direction, whereas a scalar has a magnitude but doesn't have a direction. So for a vector to be fully defined, we must include a direction, whereas a scalar cannot have a direction under any circumstance. So yeah, distance, speed, elapsed time, length, mass, and temperature. As you can see, these are all forms of measurements which have a magnitude but don't have a direction. So they fit under the category of scalars. Displacement, velocity, acceleration, and force, however, to be fully defined, must have a direction as well as their magnitudes. So these will all be vector quantities. A change in vector quantity will also be a vector quantity. It is essentially the difference between two vectors. So it's quite intuitive when you consider it from that perspective. And a change in a scalar quantity, that's also going to be a vector quantity. Why? Well, think about our direction as whether the change is positive or negative. So let's say that we have a speed of 10 meters per second, and we increase our speed by 2 meters per second. Our change in speed will be plus 2 meters per second. The magnitude of that change will be 2 meters per second. That 2 meters per second in itself is not enough to tell us whether it will be an increase or decrease. We need to know whether it's going to be up. We need to have a direction. Think of it as a one-dimensional vector in that case. Now, more broadly speaking, the list that I have provided here is non-exhaustive. If you ever need to determine whether a quantity is a scalar or a vector, consider whether it has a direction or not. If it's a broad category, like I've given, think about a specific example of that. So let's say we're trying to determine whether mass is a scalar or a vector. What's an example of a mass? 12 kilograms. We'll go with that. Is there a direction involved in 12 kilograms? No. Therefore, it must be a scalar. Let's have a look at drawing vectors now. Arrows can be used to diagrammatically represent vectors. We can indicate their magnitude by the size of the arrow, and the direction by the direction of the arrowhead. How about naming vectors? So once you draw a vector, you might want to name it. This is especially useful if you're drawing multiple vectors, so you don't mix them up, and you can easily refer to them in mathematical calculations. Or if you're drawing a diagram, so you can clearly see what's going on. So our first form of notation, we can write a lowercase letter with this symbol. This is called a tilde. We write that underneath. We generally use this when we're writing out vectors. Our second form of nomenclature, we can write it as 2 points. So here I've got C and D with an arrow on top. So capital C, capital D, arrow on top. So we often use this in geometry, and you can use this handwritten or typed. Our third form, this B, it's lowercase, but it's bolded. This is often used in textbooks and when vectors are typed up. Of course, you can't do this form when you're writing because it's nearly impossible to show that a letter is being bolded in a neat and time-efficient fashion. So yeah, if you're writing, stick to a tilde, or if it's appropriate, use a notation like this. If it's typed, it might be more suitable to just bold a letter. I might use any of these notations in any of my future videos. Just as a side note, I'd like to contrast distance with displacement, because it's something that students mix up all the time. Just something I thought I'd go over whilst I'm contrasting vectors with scalars. So let's say we're trying to get from point A to point B. We can take this blue path. We'll call this path 1. In this case, the displacement will be towards the right. You have both a magnitude, which turns out it's the length of A to B and the direction towards the right. But we can take any number of other pathways. Let's say we're taking the green pathway. Our distance will be the length of this path. Our displacement will still be the same displacement as the direct path. It will be the magnitude of the distance from A to B, and it will be in that direction, from A to B. Similarly, from taking the brown path, our distance will be the length of the path, and our displacement will be the same. There are any number of possible paths you can go to get from path A to path B, but the displacement will always be the same. And our distance will only be equal to our displacement when we take the most direct path. Now, the reason why I bring this up is because speed is the magnitude of velocity. But this result does not extend to distance and displacement. The magnitude of displacement is not our distance unless we take the most direct path. So just something to keep in mind. Now, before I move on, let's have a look at another example of displacement. So let's say we're starting at this point here, and we're going in a circle in a clockwise fashion, and we finish where we start. Here, our distance will be the circumference of the circle. Our displacement will be 0. So in this case, our distance will be greater than our displacement. So yeah, unlike how speed is going to equal a magnitude of velocity, distance can be greater than or equal to the magnitude of displacement. Being equal to the magnitude of displacement when the most direct path is taken, and greater than the magnitude of displacement when an indirect path is taken. I'd also like to quickly go over a number of different vector operations, just so you're aware of what's out there. So, addition and subtraction. This is essentially adding vectors. Turns out subtraction is adding a negative of a vector. I'll go through that in some of my later videos. Dot products and cross products. This is just more so for your awareness. If you're doing high school physics, more likely than not, you won't need to cover this. If you're doing like specialist maths, for example, however, you will need to cover dot products and cross products. But yeah, this will be out of the scope of my physics lessons. But yeah, just as an awareness thing, other operations do exist. Thus, in conclusion, a vector has both a magnitude and a direction, whereas a scalar has a magnitude but doesn't have a direction. Furthermore, vectors can be diagrammatically represented as arrows with their magnitudes given by the length of their arrows and the direction by the direction of their arrowheads. Coming up in my next video, I'm going to introduce you to vector addition. Thanks for watching, and please feel free to subscribe.